session. Hi everyone. This is again Open Neuromorphic, and today we will have Professor Jason Eshraghian from UCSD giving us an hands-on session with snnTorch that surely most of you have used or at least know in the neuromorphic domain. Again, we are a small organization. We are slowly developing, and we are basically open source enthusiasts, both from the hardware and the software side. And if you want to get involved, want to know what we do, what events are upcoming, please check out our website, openneuromorphic.org, or you can scan this QR code to join our Discord server, which is fairly active, I must say. And moreover, I want to remind everyone that we have more upcoming talks in the next 3 months, more or less, with Catherine Schumann on evolutionary optimization for NM systems. Then snnTorch will join us with 2 events with both their most recent chips, Spec for computer vision and Xylo for low power processing. And then we will have Andreas Wild from Intel to talk about the really famous Lava framework that most of you know too. And so I leave the floor to Jason. And as Jason said, you can follow along using the first Colab available in the chat. Otherwise, if you too lazy to type along, you can easily use the cheat sheet directly and watch Jason coding, hoping that nothing crash.
Nothing, everything is going to crash. But yeah, could you please resend? So yeah, I need you to do 2 things. Can you let me see post so I can share screen, and then resend the notebooks, because anyone that joined after you submitted to the chat doesn't see everything.
Okay, then I will do this. Okay, in the meantime, you can share your screen and I will fix everything.
Fix everything. Oh, awesome. Got it.
More or less, apart from myself.
How are we doing that? Can we see things?
Yes,
yeah,
I can see.
How's size? Because yeah, so size matters here, right? Are people comfortable with what this looks like? Hopefully it's large enough. I don't know, can we see what I'm typing? Fab smiling, so I think we're good. Awesome. All right, well, thanks for the intro, Fabrizio. So yeah, as I said, this is going to be super chilled. I'm going to assume a few things, that we somewhat familiar with spiking neural networks, that we're somewhat familiar with leaky, integrate, and fire neurons. I promise that I have 0 slides. This isn't going to be like a sequential presentation. There's going to be some, yeah, feel free to throw in the Q&A. Greg was asking if we can enable chat so that we can interact more than just thumbs up. Thumbs up regardless, but what would be, yeah, that could be cool. I'm very bad at multitasking, so just like if Fabrizio, if you could kind of moderate, I guess, and just interrupt me whenever, like I'm more than happy to talk less, to be honest. So yeah, I'll assume there's some prior knowledge, so I can skip going through the nitty-gritty details of history with leaky, integrate, and fire neurons, and I don't need to justify why we want to use I guess why we want to use backprop with SNNs, and of course there's cases for and against. Those are addressed elsewhere. This is just, let's get something functional, let's get something working, and depending on how we go for time, go over fancy things and see what tips and tricks we can squeeze out of some snnTorch features. So first things first, we're going to, hopefully everyone's got access to the Colab notebooks. If you find that I'm going too fast, feel free to go to the pre-filled stuff, but if you can follow along, go with the empty one and copy paste as in the same way that I do. Now, Google Colab, if you're not familiar, is beautiful because I get free GPUs. So if you go into runtime, change runtime type, hardware accelerator, GPU, I suddenly have access to GPUs, probably assuming that it is not so high in demand. So I'm going to press play, or alternatively, you can also press shift. Whoops. You can also press shift plus enter, and that's going to basically run a single code block, right? So you can see that this is installing. I'm pretty sure we automatically connected to a GPU somewhere in there. Cool, we can view resources. GPU, nothing's really being used. That's good. Then if I move to the side, so you can press this folder button and take a look at what's in your kind of base directory. So if you want to, if you need to create things, if you need to create a folder, say that's my folder with my data in it, I'll go ahead and delete that, and we can, I guess, do things as we need them. So I'll hide this section, and yeah, let's move forward. So the next code block is plotting settings. Don't worry about opening this up, but it's just a heap of code to make my life easier, so I don't need to show you how to use matplotlib. But yeah, just run that or press shift enter, and that'll be that. So as a quick overview of what we're going to talk about today, so the basics, and I'm hoping I can grind through this super fast, but just the leaky, integrate, and fire neuron, how to use it. Secondly, we're going to put a bunch of leaky, integrate, and fire neurons and a bunch of PyTorch layers together and train them using surrogate gradient descent, where we are hopefully somewhat familiar with the non-differentiability of spikes, and we use surrogate gradients as opposed to exact gradients, because otherwise no training would really take place. Once we cover all that ground, what will we do? We'll look at a couple of fancier things that are enabled in snnTorch. So firstly, population codes. Well, I guess the idea is that the brain doesn't encode individual features or concepts into one single neuron. Otherwise, the brain wouldn't be super resilient. Rather, it has these, the idea is that there are probably these distributed representations of data. And so information is encoded across multiple neurons. And with MNIST and vanilla data sets, typically our output layer, the number of neurons in our output layer is just the same as the number of classes in some sort of supervised learning classification task, right? So population codes could kind of like a more generalized version of that, where maybe we have 10 neurons per class, or we have 100 neurons per class, something to that effect. And Fab says that the chat is now active. If you want to chat with me, will I notice that you're chatting with me? I'm not sure. So yeah, feel free to flag me. And yeah, just interrupt in whatever way. But yeah. We want to make this conversational. Otherwise, I'll get really bored. Then yeah, following that, we've got leaky, integrate, and fire neurons, but there are more, I guess, fancier versions of neurons, and we'll talk about those too, such as recurrent, leaky, integrate, and fire neurons, and should maybe be familiar with long short-term memory cells. So we extended that to spiking LSTMs. Then we'll go on and learn how we can integrate precise spike timing. And this is where my notebook gets a bit sloppy and I haven't had time to proof check it all, but hopefully we'll figure things out. Classically, these backprop methods usually train networks to fire in kind of like a rate code rather than learning exact timing of spikes. So hopefully we can get a feel for how we might get started on training neurons that can fire at a precise time point. Then a bit on hardware-friendly training, weight quantization and the hidden state or membrane potential quantization. Then if there's time, I don't think there will be in this session, so we can always organize something separately in the Discord or just do something super casual. But yeah, so SNNs, as power efficient as they are on neuromorphic hardware, they are a bit of a pain in the ass to train, right? I found that when you compare them to non-spiking networks, it kind of makes sense, right? Because backprop and all that stuff has been designed with non-spiking networks in mind. And so the hyperparameter space of functional SNNs is typically far more constrained than its non-spiking counterparts. So if we can kind of help alleviate some of that trial and error of setting different architectures or setting different decay rates of neurons using hyperparameter sweeping tools. So Optuner is my go-to. There's also Raytune. Let's see if we have time to get into that, but yeah, we'll see. I promised Fab that I'd make this a make this joke. So if we import snnTorch's lava DL, no, I'm not going to do that. So what is the Discord link? I'll let Fabrizio shoot that into the chat. So there's an Open Neuromorphic Discord link, as well as an SNNTorch specific Discord link. I think that Open Neuromorphic is more general, so that's a good place to start. So let's do our imports, right? Let's run all of this junk. So we're going to import SNNTorch as SNN, spiking neural net, then spike plot, which I just call splat, like some dirty little functions to help with figures and plotting, import PyTorch, then import matplotlib, and then IPython to get some pretty figures in the, in the notebook environment. So let's build a leaky, integrate, and fire neuron, right? Cool, one line of code. If you want to get into the details, I'd recommend checking out the tutorials. Actually, yeah, I'll very quickly show you the tutorials if you do want to go there. So yeah, just go into the SNNTorch documentation. You can get there by Googling SNNTorch. Scroll down, see tutorials. And yeah, there's just a shit ton of tutorials that go into this in probably a lot more depth than you need. But yeah, if you want to go into the background of the LIF neuron, it's a whole heap of code that you can play with, a bunch of math that you can skip over or look into more detail if you so desire. So that's yeah, a good starting point if you're just getting into it. But let's assume we are comfortable with those principles and just build a leaky, integrate, and fire neuron. So the syntax for leaky, integrate, and fire neuron is unsurprisingly snn.leaky, right? And there's a fair few arguments in there. The most simple leaky, integrate, and fire neuron that we can possibly define just has one argument. And here it's beta. Beta represents specifically an inverse time constant. Alternatively, it's just a decay rate. And we'll see exactly what that means, but it just defines the decay rate of the neuron's membrane potential. So I'll go ahead and run that. And bam, we suddenly have a leaky, integrate, and fire neuron kind of embedded within, within this, within LIF, right? So we now want to pass a bunch of things to LIF. Let's see if I can draw using my mouse. So imagine we have some input X, we have this neuron, we have LIF, and there's some magic going on inside that membrane potential that I described before. And then, then the output, if this membrane potential reaches some threshold, if it gets excited enough, then it's going to trigger some output spike activity, right? And the spike is either going to be a 0 or a 1. So that's what this LIF neuron is doing. How do I delete all of that? Got it. That's the intuition, right? So let's actually simulate this guy. Because this is a time-varying process, we need to define the number of time steps that we want to simulate. I'm going to arbitrarily pick 200 because I like the number 200. Then we want to throw in some input stimulus, right? We want to excite the neuron in some way. How can we excite it? There's virtually an infinite number of ways we could excite it. We could apply like an input spike. We could apply a step current. We could apply a constant current, whatever. It doesn't really matter. Let's just get a qualitative feel for what all of this is doing exactly. Let's I don't know, let's do a step current. Yeah, let's do this kind of like step pulse shape. So what's kind of made up here? Got a bunch of zeros, then we have some higher value, and then a bunch of other zeros. So our X is going to be three tensors concatenated together. Let's say, so we'll start off with the zeros. So I'm going to generate these things first. So we have 10 steps of nothing. Then let's say, I don't know, what should we do? So torch.ones, let's do one. Let's do 20 steps of ones. And then because I've got 200 time steps, I've used 30 of them now. So I have 170 zeros left. And I need to kind of combine all of these together in torch.cat. Okay, so let me clear all of these drawings. Then is this right? And I think that this all needs to go into a tuple, right? So this all is sort of combined together into one, I guess, 1D tensor with zeros and ones and zeros. Let me reduce these ones a little bit. So let's say that I want a current step of like 0.1 amp. So I'll just multiply the ones by 0.1. Then I also, because this is a time varying process and we have initial conditions, I need to initialize my membrane potential of the neuron. I'm going to just initialize it as a 0. And likewise with my spike. So assume that we do not have any spiking. I just got a new keyboard, so bear with me. So many typos, and I'm going to run that. No errors, perfect. So next, let's actually do some simulation. All right, so we have, I've already kind of put memrec. So mem recording is just an empty list. And we're going to, over time, for every time step, we're going to populate that list. We're going to, every time we calculate a new value of the membrane potential, we're going to append that to the membrane recording and just sequentially expand these lists. So we've got the membrane potential and the spiking list. Then again, because this is sequential, we'll move this screen sharing thing down. We need a for loop to iterate over the time steps. So for step in range num steps. What do we want here? So we want the leaky, integrate, and fire neuron loop. So like I said, leaky, integrate, and fire neuron is going to take some input, right? It's going to, we've already defined our input as X, but X has multiple elements. So we need to iterate through each of those elements. And we do that by indexing using step. So that'll scan across from 0 to 200, from the 0 current input to the, what did I say, the 0.2? Yeah, 0.1 amp current input. And then it's going to kind of die again, back down to 0. So that's one input, but we also have to initialize the membrane potential. So we pass in mem, which is just a 0 there. And so the leaky, integrate, and fire neuron is going to return 2 values. It's going to return the output spike. And secondly, it's going to give me an updated membrane potential, right? That's it. That's like a single pass of a leaky, integrate, and fire neuron. And we just loop through that again and again. We keep updating membrane. But like I said, we want to store it in this recording list. So what we do is memrec, and we just append the membrane there. Likewise with the spikes, we want to plot the spikes over time. So spike rec append spike, and that's all dandy. Now, because in PyTorch, we like to accelerate things, we like to load up large lists of numbers onto CUDA, we want to put them onto our GPUs. We will actually convert these lists into tensors or just higher order matrices. So we can do that by calling torch.stack and passing a list. And I guess whatever the sequence of list is, that is going to be turned into the 0th dimension of your tensor. So it's just kind of like adding a new dimension in a tensor. And we can do this with any size tensors, or as long as it fits on your GPU. And I've already included this function here just to plot this stuff. So hopefully this works. Let's see what happens. Awesome, we got something. So we see at the top, that's my input. Zeros, a bunch of 0.1s, and a bunch of zeros. Now, while this input stimulus is being applied, we see that the membrane potential, or the hidden state of the leaky, integrate, and fire neuron, is going to exponentially relax towards some steady state value. But then once we kind of kill this value, once we kill the input excitation, it then exponentially relaxes back to some steady state value. Now, this dashed line, why is it updating Adobe Lightroom? Get out of my face. So as this membrane potential is increasing, we see that there's some sort of threshold, right? So the spike activity of a leaky, integrate, and fire neuron is determined by this threshold. And we need this excitation we need the membrane potential, or the hidden state, to reach that threshold in order for spiking activity. And we can see that here the threshold is about twice the value of the membrane potential's peak. So this clearly isn't enough for any spikes to be generated. And if we were to construct a network, there would be no spikes being triggered to downstream layers. So let's scroll up and maybe change our input a little bit. Let's crank it up. I don't know, 0.2. Let's see what 0.2 does. Okay. Oh, is that It's almost hit 1. I think it's just under because we see no spike. So I'm going to iterate a little bit and take it to 0.21 and rerun the simulation. Yes, there we go. So we now have a single spike and we see a bit of a reset. So we get a sharp drop. There's various reset mechanisms. There's reset by subtraction, where you subtract the threshold. So you would see the membrane potential subtracted by 1. There's reset to 0. So in that subtraction case, let's say that we offshoot and we overshoot the threshold, and we subtract it by 1, the threshold. There is reset to 0, which kind of clamps the membrane potential right back down to 0. What you see here is kind of like a soft reset. So the default method in snnTorch uses this threshold scaled by your decay rate, beta. So previously I defined beta to be 0.8. So the subtraction is going to be 0.8 here. And the reason we do that is just because it seems to work better on a bunch of data-driven tasks, right? We were honestly not too sure why yet. The theory of this stuff is a little bit lacking, but it works. So that's our default, and you're at liberty to kind of change that around yourself. Let me do some more fun things. So let's crank up this torch.1s to like 190. And I'm going to get rid of the final 0. So this time it's like just applying a step that doesn't go back down. And I'll simulate that. So we should see more spikes. Yeah, perfect. So that's what we see. We see a reset, then it goes back up, and then it goes down, and we reset it. We trigger a spike. All well and good. Any questions? I want to fly through this shit. I think we're good. I mean, feel free to just like talk and give more thumbs up if you really, really want. So cool. With the Leaky integrate and fire neuron out there, I guess we're ready to move on and actually do something useful with it. Let's train an SNN classifier. And what did I say? I said that we'd get through this in 5 minutes. It's more like, damn, 20 minutes. That sucks. We've got the worst concept of time. So we're going to move forward with the SNN classifier in 10-ish minutes. That's totally going to be like half an hour. Anyway, so we import a bunch of functions. Torch.nn has all of the base PyTorch layers that we want. Data loaders so that we can actually load data. We're going to start with the MNIST data set, and just because it's quick, but it also kind of is a little too basic. So we might want to play with a little bit more complex stuff, and hopefully we'll get there using Tonic in a bit. And then we want to transform that data. NumPy is great. It's got some nice functions in there, so I'll import that too. And iter tools, which lets me iterate over samples of data as well. But this is all boilerplate, and I've just left it in there because it's just a pain in the ass to keep typing out. I'm going to use a batch size of 128. So my full data set's going to be divided up into bite-sized pieces. Each of those pieces will have 128 samples, and then those 128 samples are going to be fed in parallel to my network. I'm going to download the MNIST data set into this directory, so that'll be created automatically somewhere. Actually, I think it's going to be created. You won't see it in this here, but it's going to be in the parent directory. We use floats, do mixed precision and other fancier tricks if you wish. If you have a GPU, then your device will be set to CUDA. If you have a CPU, then it'll be set to CPU. And if you're running this locally on Apple Silicon and you have a GPU in your M1 or M2 MacBook, PyTorch recently updated this little feature. So MPS, Metal Performance Shader or something like that. I don't know what it stands for. But yeah, that works now. I think that's a very specific version of PyTorch that you need to get that working. But yeah, so let's run all that junk. Define a transform. So I just want to transform my MNIST data set. MNIST is just a series of handwritten digits. So I want to ensure that it's 28 by 28. So 28 pixels by 28 pixels. It's a single channel image. So it's grayscale. We're going to convert it to a tensor, and then we're going to normalize all of our values to fall between 0 and 1. Neural networks like those numbers. The way we initialize weights, it's a good idea to normalize things between 0 and 1. Then we load the MNIST train set. We load the MNIST data set test set. Train equals true, train equals false, and shift enter. And that runs, that downloads, very, very quick, very nice. And we put those train sets into data loaders so that we can do this whole parallelization and load data in neat little batches. Feel free to, like, I guess, pay closer attention to these arguments on your own time. We shuffle the data set. And if you have it, because we're dividing data sets of 60,000 by 128, if you so wish, you can drop the leftovers. It doesn't matter too much, to be honest. So I've already run that. So let's actually, I don't know, construct a fully connected spiking neural net, right? Let's do some fun stuff. So we're going to start off with just a fully connected network, and we'll get to convolutions in a bit. But the number of inputs is, like I said, the number of inputs to my network should match the number of pixels in my MNIST data set, right? So we're going to take that square, we're going to take that 28 by 28 image, and we're going to kind of roll it all out, right? We're going to roll out those, what's 28 by 28 is, pretty sure it's 784. I've done this enough times to, yeah, perfect, 784. So our input number of inputs is 784. My number of hidden units can be whatever the hell I want, as long as it fits on this GPU. Let's say 1,000. I'm really hoping my GPU environment doesn't die on me. The number of outputs, there's 10 different digits from 0 to 9. So we have 10 output neurons. And the output neuron that spikes the most frequently is going to be the one that we predict is I guess, is our prediction. Number of steps. Previously, I said 200, but now we're working with actual networks. Previously, it was just one neuron. Now we have various layers. I do not want 200 time steps here. I'm sure there's probably enough memory on consumer grade GPUs to handle that, but I just want quick simulation. So we'll go with 25 steps. My beta, previously we said 0.8. Now, if I change that 0.8, it's going to decay at different rates. So we saw that rise time and we saw that decay exponential relaxation. This time I want data to be sustained for a bit of a longer time. I want the decay to be slower. So 0.95. And what that means is that at every time step, we're going to see a 5% decrease of the membrane potential from the previous time step. When beta was 0.8, we saw a 20% decrease of the membrane potential for every sequential time step. So let's initialize all these parameters. And then we want to define a network. So let's do that. So we're going to define the network just to be net with a capital N. We're inheriting from NN.module. There's a bunch of nice functions in there from PyTorch that let us train these networks far easier, but we need to initialize our layers first. Before we consider what the forward function does, before we consider what happens when you pass data into this model, we need to actually say what the model is, right? So that's what initialization is for. Actually, I'll draw it up real quick, right? I'm going to have, drawing with a mouse, terrible. So we're going to have an input. That's going to be 784 neurons. So there's a question that's been raised who's asked me to run the same MNIST example on a few convolutional layers, so 5 to 6 conv layers followed by 1 to 2 dense layers, but RAM consumption is greater than 70 gigabytes and cannot run on any normal GPUs. So for that, you need data parallel. You need to distribute that model across multiple GPUs. I won't cover that here because Colab's environments do not allow me to do that on a free, on no subscription. But that is a good point for a future tutorial. We'll keep that in mind, yeah, because distributing data across multiple GPUs is important. And we recently fixed that up in snnTorch in the last 2 updates. So yeah, we've got 784 pixels in this image, and we're going to kind of take this pixel, throw it into this neuron, take this pixel, put it here, this pixel here, etc. And then this is connected to our hidden layer. Actually, I think I said my hidden layer was 1,000 neurons. And then my output layer is 10 neurons. So this is what a normal vanilla fully connected network would look like. And so for that, you would just say fully connect. My first fully connected layer would be a dense layer, NN.linear. Let me move this to the side. NN.linear. So have I defined my number of inputs and my number of hidden? So this is this is 784, this is 1000. Then, like I said, in a non-spiking network, we would just do this, and then we have an output layer where I have num hidden, num outputs. And yeah, I should say all of this with the caveat that this is relatively bad coding practice. I'm like getting the number of inputs from a global variable. It's generally better to put everything into the same spot into, I guess, just a much neater, running from Python scripts rather than Colab. So another question is, since there is only one image fed into the neural network at a time, won't the time step be 1? Good question. I haven't gotten up to that, but what I'm going to do is just pass the same image 25 times. So my num steps is 25. I'm just going to pass the same image 25 times. That's kind of like having a constant current input where the current value is just the pixel intensity of the image. So then to actually make this spiking though, we're going to treat the output response of this layer to be, I guess, the input to my spiking neuron. So that's kind of like getting a vector of, I suppose, LIF neurons. And we're going to do the same thing. Well, I guess this should actually go here and here, right? So I can erase this because this is the flattening. This first layer is the flattening of our input image. So the way that we instantiate these spiking nodes is just like before, self.lif. Now the question, do we need to convert our raw MNIST image vector to a spiking one? The short answer is no, right? It doesn't need to be 1 or 0 because spiking neurons can accept continuous current values. And in a way, I showed that over here, right? So my input current was 0.2 rather than 0s and 1s. So it's just a difference in, you just observe different dynamics by applying spikes versus not applying spikes. Then the next question from Mike is, can we increase the number of hidden layers and decrease the number of nodes in each hidden layer? Is it feasible considering spiking neural nets and the convergence rate? Yes, you can do whatever you want with your hidden layers. So the convergence is always a little bit more challenging with spiking neural nets as against, as against non-spiking networks. But yeah, it's just, you treat it as a hyperparameter the same way you would a non-spiking network. So with the Leaky integrate and fire neuron, what am I going to do here? So exact same thing as before, right? My SNN.leaky, I've already defined beta to be 0.95. Then let's do LIF2 equals SNN.leaky, beta equals beta. Now, what's kind of neat here is, so what we're going to observe is FC1 is our first fully connected layer. That's going to generate some activations. Those activations are used to trigger spiking in SNN.leaky. Now, previously, I showed what happens with one input injection into the LIF neuron. This time, we have 128 batches, and we have 128 samples at a time, and we also have that being passed in parallel. That means that LIF1 is going to look something like 128 neurons in parallel with 784 spiking neuron nodes. And we're going to see LIF2 is, I guess, this number of outputs as well. So there's going to be 10 output neurons that kind of repeated for the number of batches. We don't need to consider that because the way I've done this is we automatically in the background infer what the shapes and sizes of these layers should be in terms of batches. Another question is VTH a learning parameter? So is the threshold a learnable parameter? Great question. That's up to you. So I have by default set the threshold. Let's see if this comes up. Threshold is by default set to 1. I can parameterize that to 5. I can parameterize it to 10, 0.1. So if you find that your network is not firing sufficiently, like if you see that your network isn't training, then the first thing I do is observe the spikes at the output. So I just take my spike recording and sum it all together. If it's 0 or if it's a very small number, I'll then drop the threshold of my layers, and that'll typically foster a bit more spiking and therefore learning. Yeah, if there's no spiking between layers, then there's no pathway for gradients to flow during the backpropagation process. So threshold, I can parameterize that. Alternatively, if I'm happy with the threshold being set to 1, then I will set learn threshold, I think, yep, to be true. So that is what's going to enable your threshold to be a learnable parameter. By default, it is false. I haven't really seen any papers that effectively use learnable thresholds. I don't really have any comments. I just don't think that it's shown itself to be useful yet. But yeah, the rate of research coming out is insane. So maybe I've missed something. So yeah, if anyone knows of something else, then please do bring that up. Cool. Let me think. Is there anything else? Oh yeah, of course. So I mentioned that we want to have so SNNs, Leaky integrate and fine neurons. Alex Henke said that we've used it. Yeah, we did use it, but did it help? Like, did we do an ablation study? I don't remember. Yeah, you guys can talk in the chat and I'll keep an eye on it. So yeah, shit, what was I saying? That's right. Spiking neurons are non-differentiable, right? If the act of thresholding a function is non-differentiable, so we use surrogate gradients. Now, by default, we use a surrogate gradient of we take the derivative of the arctangent function, and that works really well. We do not know why. So that is what we use. And full credit goes to Feng Wei, who's the developer of Spiking Jelly. I think he might have pitched that in one of his spiking ResNet papers or learnable parameter papers. He does really good work though, so I strongly recommend checking out his stuff too. But yeah, we use the arctan function by default, but you can always reparameterize it by updating spike grad. I wouldn't bother, to be honest, but if you do want to play with it, I would say from snnTorch import surrogate, and surrogate will give you access to a bunch of surrogate gradient functions. So I could say spike grad equals surrogate.fast sigmoid, which is something that we're all quite familiar with. But yeah, like I said, by default, we use arctan. And so yeah, there's a few parameters in here that you can play with, like alpha equals 2. So whatever. I'm not going to touch that though, because the default settings work pretty well. Awesome. So any questions on instantiating neurons? We're good. Normally I'd wait and like pressure everyone for questions. So learn thresholds is very useful for ANN to SNN conversion. So thanks, Marco. I did not know that. The more you know. Damn, that's neat. Yeah, Marco, send me a paper on that. That'd be awesome. Yeah, thanks for letting me know. Also, I remember Bodo mentioned that the reset mechanism that you use is also quite important for the conversion conversion process. So wait, so I can change the reset mechanism here. So by default, we have that subtraction method, reset by subtract. You can clamp it to 0. You can also say none. So there's no reset mechanism either. That's not going to promote sparse spiking activity though, which means more power consumption if you're running on neuromorphic hardware. Sweet, so we need to, once again, actually, I'm going to clean this up. We need to initialize our membrane potentials. I'm going to run this again, just so I don't kill my runtime because of lack of use. So previously, we just set it as torch.zeros, and that was fine. But remember what I said about the shape of the leaky integrate and fire neuron? Like there's no way that LIF2 knows how many samples of data we're using. It doesn't know what the number of outputs from the previous layer there are, and therefore it doesn't know the number of inputs coming in. So there's a neat trick that we have where we just take a function that's stored within LIF1 called init leaky. So just initialize leaky. And what that's going to do is kind of set up a tensor with a flag that says, I have no idea what I'm doing. And then the moment we simulate it, this tensor is going to go ahead and match the size of the input excitation. So this is a neat way to not have to worry too much about a lot of those things. So we do that with the first membrane potential layer and with the second membrane potential layer. Axon delays, yeah, AJ is asking, Are axon delays learnable? No, we have not integrated that. There has been some talk about it in the snnTorch Discord. I haven't had time to look into it. I think there was someone that implemented a function in their own time, but it would be really nice to see that integrated into snnTorch by people that are more competent than me. Are decay parameters learnable? Hell yeah. Let's see, so unsurprisingly, much like learn threshold, learn beta. So that's how we do that. And also, I should mention that there's no reason why beta needs to be a single value either. So previously I set it to 0.95. I am at perfect liberty to set it to, well, let's say I want to do beta 1. So beta 1 for LIF1. I can say beta 1 equals torch.rand. What's the size? The size should be num hidden. Yeah. I can have an individual decay rate for every single neuron in that layer as well. And then if I say learn beta, each of those individual neurons are going to have their own learned parameter. So yeah, you can play with all those things. Thanks for bringing those up. I just kind of forgot. It was like 2.5 years when I started putting those features in. Awesome. So we want to record the final layer. Yeah. Keep the questions coming. I'm loving this. We instantiate an empty list to be the recording of our second spiking activation, so the output spikes. We do the same thing with the membrane potential, an empty list, and then we need to do a time loop. You know what? I'm going to delete this and we're going to write this from scratch. So it is a little bit tedious, but once you've done it once, then forget about it. Then you can just leave it. So for step in range num steps, which we define to be 25, perfect, 25, we're going to first run the fully connected layer. We're going to take in our input, which I've defined to be X. This X should also be flattened, right? Because the X that's being passed in is 28 by 28. And we want to flatten that to be 784. And the reason I put in this 1 here is because the first dimension of MNIST is going to be the batch size. And we don't want to flatten the batch size. We want to keep the batches separate and intact. So we keep the batch the way it is. And so we only flatten the first dimension after that. So more concretely, the dimensions of MNIST are going, the data coming in is the batch size, which is 128, times, I guess, the X dimension, which is 28, times the Y dimension, which is also 28. So we're flattening from here onwards. I guess we could say the channel size is in there as well, which is just 1. So if we flatten from the first, so this is the 0th dimension. If we flatten from here onwards, we then get 784. So we flatten from there and we can pass 784 inputs in parallel to our network. There was a question in there that asked for resources to something. Resources for surrogate gradients. Yeah, there's tutorials that kind of cover that. It is kind of easy, I think. Let's see. So if I go back into the snnTorch docs, then I go down to, give me 1 second. That's right, surrogate gradient descent in a convolutional SNN. You can open that in Colab and you'll be able to see how you can mess around with different surrogate gradients, or if you want to understand the theory a little better, I would, strongly recommend just going there. And hopefully someday we can use SNNs to control robot arms. Actually, no, that's already a reality. A bunch of people are doing that. So Gabriel is asking, George's last talk mentioned learning continuous data, but it would need to change a little bit. Here, we're feeding the same image in at 25 time steps. Could that then potentially allow the forward training approach? Honestly, I have no idea. I don't know the forward approach well enough. I'll need to refresh my memory to give a well thought out answer to that, but it would be cool to integrate that kind of stuff with SNN, as I don't think we've done that yet. My money is on like in 2 weeks time, we'll see forward learning and spiking neural networks on archive. So yeah, back to it. We're passing in our input data that's been flattened into our fully connected layer. That returns some current. I'll call that current 1. Then we're going to pass that current as the input excitation to my first Leaky integrate and fire node, right? So it's kind of like we're concatenating a dense layer with a spiking unit or spiking vector of units. And we're going to excite it with current 1, but we also need mem1. We need the initial membrane potential. And that's going to return 2 variables, like I said. So spike 1 and mem1. And spike 1 will be 1 if the membrane exceeds the threshold. Spike 1 will be 0 if membrane does not exceed the threshold. Then we kind of just repeat this, I guess, but with different layers because we have one more layer. So current 1 becomes current 2. Self FC1 becomes FC2. We no longer need to flatten anything because spike 1 is already in the correct shape. So I'll delete that. And then LIF1 becomes LIF2. Spike 1 becomes spike 2. Blah, blah, blah. Current 1, current 2, because we're passing current 2 here. And now we're using this initialized value of the membrane potential. Then is that all? No, then we have to append. Yeah, so we then want to keep track of these values that change over time. So we store them in this list. So for every single loop, we take, so store in list. We take the list of the recording of spike 2 and we append the latest value of the output spike. And we do the same thing with the output membrane potential. How we use that is what we're going to kind of address next. But then we return tensors. We convert these lists into tensors using torch.stack. So we're returning a tensor of spike 2 of the output spikes and a tensor of these of the membrane potential. And so the dimensions of these will look like the number of time steps, which is 25, by, I suppose, the number of outputs, which is just 10. Oh, and we have batch size in there as well, which is 128. So that's what our tensor is going to look like. Now, I'm going to go ahead and run this, and this will take a moment because we're loading up the network onto CUDA, because I'm pretty sure I set my runtime to be GPU, and I'm hogging a GPU and hardly using it. So now our network is stored in net with lowercase. Shit, did I say I'd get through this in 10 minutes? Damn, you really got to sort out my time management. All right, so the loss function, we're just going to use a cross entropy loss. Optimizer, we like to use Atom because we know that it works. It's a really good kind of first port of call for SNNs. And I've seen most tasks obliterated by the Atom optimizer. There have been a few corner cases. So I think one of my incoming grad students, Ruigia, observed that stochastic gradient descent with momentum outperformed Atom on larger architectures. That was pretty cool. The learning rate arbitrarily, I'm using this because I know it kind of works. And let's leave betas, the optimizer hyperparameters, to be what they normally are. And I don't want to waste too much time on this simulation. So I'm just going to say number of epochs is 1, counter is 0. I don't want to rewrite this from scratch. So let's just go through this line by line. So counter is going to count the number of iterations that we're at. So number of epochs is going to be, so we've got 60,000 data samples, and then we have 128 samples per batch. So that's going to be like 400 and something. I don't know. Off memory, I think it's 468 with some left over. So 468 iterations, and we're going to count through those iterations to keep track. So Fabrizio is asking, what if we fully unroll that loop for time steps like with RNNs? How bad would that hit GPU memory, and how much faster would inference be? Yeah, this is also really important, right? So what I have done is sequentially pass data in the same way that the real world would kind of handle it, right? You take data in, you pass it through your network, then you iterate to your next time step, pass your next sample of data in. Of course, this example doesn't really show it because we're passing the same image at every time step. But let's say I have a video, right? If I had a video, and I will show you an example of that, then I would need to iterate through the various time steps of my input. I would need to first sample into the first frame of my video, then the next frame of my video, then the next frame, and so on and so forth. And actually, that's what Spiking Jelly does, and they get incredible speed as a result. So what they've done is kind of like unrolled this neuron over time. So you pass in all of your inputs at once, all of your inputs over time and over batches, all at once in parallel. Then you get the output activations across all time steps, pass all of those into your Leaky integrate and fire neuron nodes. At once, you accelerate using, I guess, custom CUDA kernels. And then once the entire time step of the first layer is done, you then do the same thing with the next layer. So they've been able to optimize their networks incredibly well. Actually, yeah, so again, Ruigia tested this out on a semi-large scale language model that we released. It's got the funniest name, so Spike GPT. And we could only train that in a reasonable amount of time, thanks to spiking jelly. So they've done incredible work on that front. The challenge with that approach is that it kind of eliminates the possibility of doing online and continual learning and doing kind of variations to your network. So it's kind of like trading off your ability to parameterize your models with performance. So if I want to get highest performance in the shortest amount of time, hell yeah, I would jump straight there to spiking jelly because beautiful work. Then moving forward, let's see. Okay, so number of epochs, 1, 468 iterations, and the count is going to count through those. For epoch, well, this isn't really a for loop. If I'm just iterating through it once, I will convert my train loader into an iterator. So we're going to iterate over 468 samples. And each train batch is going to have data associated with it. So the data is going to be like those bite-sized pieces of 128 samples. Each of those samples is going to have targets associated with it. Those targets are 0 to 9. It will tell me what index my picture, or what the target label of that image should be. We load data and targets onto CUDA. We set this net flag to train to say, hell yeah, time to calculate some gradients. Then we pass the data into our network. I can delete this because I'm pretty sure I already put flatten into my model. So we don't want to flatten things twice. Otherwise, we'd probably get shape errors. And remember, my network is returning 2 variables, a tensor of my spike recordings over time and a tensor of my membrane potential recordings over time, right? So I'm going to return my spikes, but I don't need my membrane, right? So I'm just going to leave that. If I did want to use it, I could, but for now, I'm just going to ignore it, set it as an underscore, leave that as that. We need to optimize for some objective as well, right? So let's initialize a loss value to just be 0, right? So 1 element of 0, load it up onto your device. And then for every iteration, I'm going to calculate the difference between the targets and the spike recording. So what am I doing here? Remember, my spike recording had dimensions of time steps times batch by number of outputs, num out. So 25 by 128 by 10, right? Now, what I'm doing here is summing in the 0th dimension. So I sum up, so I have this tensor of time, I'm smushing it together. Everywhere there is a 1, it just kind of accumulates in a kind of counter-esque kind of way. So I get rid of the time dimension. What does my spike recording now say? When I've summed up in the time dimension, I now have a tensor that tells me the spike count. So previously it was 0s and 1s. When I sum them all up over time, I now have the spike count of 10 neurons for 128 batches. So 1,280 neurons. I have the spike count for each of those 1,280 neurons. Then I compare them to my targets because I'm trying to get the correct neuron to fire the most frequently. And that's kind of handled using the cross entropy loss. And by minimizing that distance, I then will get a loss value for that iteration. I will update the loss value. So plus, I guess, don't really need to instantiate anything, or I think we could just set it to be plus rather than plus equals. Then optimizer, so we zero out our gradients. This is just kind of boilerplate for training a model. So we zero out our gradients. We run our backward pass to calculate the new gradients, and then optimizer.step will do the actual update using said gradients. I deleted this, so yeah, best practices, you'll want to keep track of your loss. So I don't want to do that because I'm in Colab. and I want to print out my loss or some metric. So I'm just saying if my counter, so for every 10 iterations, I'm going to spit out what iteration I'm at and the value of my loss. And so I say dot item just because my loss value is one number. Like I've taken all my batches and all my neurons, smushed them into one loss number, and I take that out as a single floating value. And I update my counter. And here, look, I'm just going to go through 100 iterations. I don't want to wait. So if we're all ready, I'm going to press Shift Enter, and hopefully no errors will be thrown at me. So we're going to run through this simulation. And hey, yeah, we see something functional. We see the train loss is 2.5, and it starts kind of plummeting down, which is nice. That's cool. And then we've early terminated our training process after 100 iterations. So next, I just have this function to measure accuracy. Model. So this is in a function called measure_accuracy. Oh yeah, if like I said, if there's any questions, then throw them my way. Like it's all is good. You can be as comfortable, or not without being too comfortable, be as comfortable as you want. We set this flag to say we want to now evaluate our model, which pretty much kills the gradient calculation process. So that's all cool. To measure accuracy, we need two things. We need the total number of correct predictions, and we need the total size of our data set. So I'm going to put these variables and update them over iteration. So running length, start at 0, running accuracy. Well, before we've done any experiments, we have 0 correct predictions, right? We do our iteration loop like before. So we take our data loader, get our data and our targets. We pass our data into our model. I'm going to delete flatten again because we already included that in our forward pass from the net model. We don't need membrane potential. And so what we're going to say, a good question that I had no idea. Is it possible to mix this library with those related to Bayesian neural networks like PyMC3 or Pyro? I've never done it. I know Alex Henke's, who I think he's lurking in this group right now, he might have some more experience with Bayesian neural nets than I do. If it's written in PyTorch-esque or NumPy syntax, it should be possible to interface these things together, but I have no idea. Yeah, Henke's, or if anyone else is more familiar with these packages, yeah, go in. So yeah, the easiest answer is if it's compatible with PyTorch, then it should be compatible with snnTorch. So we now want to do a forward pass. We get the spikes. We want to get the spike count. Same thing as before. Now we have, so what is spike count? Spike count is, and I keep putting these periods in, batch size times num outputs. So what our goal is, so each of these targets is going to have 128 samples, right? We're going to have 128 numbers telling us which label is associated with those 128 pictures. So we want to call the function max on the spike count to take out the first dimension. So batch's 0th dimension, we want the list of maximum numbers from the number of outputs. So between 0 and 9, we've got 10 neurons. We want to know which of those neurons has the highest spike count. And that max function will return two things. First, it's going to be the actual spike count. So say one of my neurons is spiking 25 times, then this number will be 25 along with all the other batches, right? In addition, it's going to give me the index of that 25 spikes. So say my third neuron spiked 25 times, this index will say 3, right? And that index is what we want because it's that index that corresponds with the targets. So the targets are from 0 to 9. Our outputs are from 0 to 9. So we're going to see how many times do these two things equal each other, right? If everything is correct, this would equal, this summation would equal 128, right? So we're going to have 1, 1, 0, 0. So how many times do these things equal each other? Now we sum them up to get the total number of correct classes for a single batch. We loop through these things, so we're going to get a running length that keeps updating over time, and by the end of our simulation, we'll have the total length of the test set, accounting for the fact that we dropped a small portion at the end because of the data loader arguments. And then we'll also do the same thing with accuracy. So we just kind of keep building up the number of correct predictions we have. Then to actually get accuracy, we take our running accuracy, divide it by running length, and then return the accuracy. So let's run that and we print this out. So I'm going to test this on the test set now. Might need to wait a moment, and it's going to be kind of, it shouldn't be, oh, okay, 93%. That's pretty good for something with 100 iterations. In theory, I'm pretty sure it's easy to get like a 98% with a bit of parameter sweeping and a bit of optimization. So that's cool. That's cool. Could always do a bit better. So let's play around with a convolutional SNN. I'm going to fly through this, to be honest. So let's initialize our layers. So let's say the first layer is a conv1, conv2d. So we want to pass how many, so the first argument is the number of channels. Our MNIST data set has 1 channel. We can arbitrarily set the output channels, I'll say 8, and the kernel size to be 5. I don't want to think about dimensionality too much, so I'm going to say padding should be same. So the input image should equal the XY dimensions of my output active or output feature map. And then I pass that into a Leaky integrate and fire layer, just like before, SNN.leaky, beta equals beta. I'm just going to leave that there. Then let's do max pooling, self.mp. So max pooling will reduce our XY dimensions, max pool 2D. So, a 28 by 28 image would then become 14 by 14. So that's kind of like the first convolution, spiking convolutional block right there. Let's just do that again. So conv1 becomes conv2. This is like our second layer. This conv2d needs to have 8 input channels because whatever that's coming out of this here is going to match the previous layer's channel size. Output channels, I don't know, 24, just whatever. Kernel size, let's keep it to 5. Padding, do the same thing. Everything else can remain as is. Then after that, we're going to flatten the feature map that comes out of the second time we max pool. And we want to pass that into a dense layer, NN.linear. So what's that going to look like? Well, we have 24 output channels, right? So 24 output channels. But then that's going to be 24 of XY dimensions. And we want to figure out what those XY dimensions are. Conv2d preserves the XY dimensions right now because I said padding should be the same. Max pooling is going to take a 28 by 28 image and make it 14 by 14. Then we're going to do that again to make it 7 by 7. So the number of values we're going to get here now, so fix that up. The number of values is going to be 24 channels by 7 in the X dimension and 7 in the Y dimension. And that should be the number of inputs I need in that linear layer. We're still on MNIST, so that's 10 outputs, self.lift3, so the third spiking layer, beta equals beta, so just treat that as being much the same. Initialize hidden states at t equals 0. We've already got code for that. I'm going to scroll up to my first neuron, sorry, to my first network and copy paste the init leaky function. I also need one more. Whoops. One more. So mem1 becomes mem3, lif1 becomes lif3, record the final layer. I don't know why I deleted these. We just need empty lists. For step in range num steps, in the interest of time, I'm going to copy paste from my cheat sheet. Right, so we pass the input image. We're passing the same input image over and over again to my conv layer. Previously, we had a flatten function. We no longer want to flatten it because we're using convs. So convs needs the 3-dimensional structure, that 1 by 28 by 28 structure of an image to be preserved. So we don't flatten it. Current 1 is generated. We pass current 1 to max pooling as the input excitation to the Leaky integrate and fire neuron. We also pass the hidden state initial variable membrane potential mem1, and that's going to create a spiking value, and it's going to update the membrane potential at the we then take spike 1, pass it into conv2. I'm getting a signal saying my internet connection is unstable. God, I love Santa Cruz and living in the mountains. Spike 1 goes into conv 2, generates another current value. And we just do the exact same thing. This time we take spike 2 from the spiking output of the second layer. We flatten it in the first dimension just for the same reasons as before, because we want to preserve the batch size and we want to flatten the 7x7 by channel size 24. And we pass that into the fully connected layer to generate another output feature map. And then we have LIF3, so current 3, mem3. Spike rate, and then we store these things in a list, and we've kind of seen all of that happen before. Now, there was an important question of, I want larger networks, I need more deeper layers, but my GPU just isn't big enough. A few tricks to address that, kind of going off script here. What I would do, a few things, right? So firstly, reduce your number of time steps. That's kind of the most obvious thing, but sometimes you can't afford that. Sometimes your data samples are just too long. Second option that you have here is to use truncated backpropagation through time. Truncated backprop through time will run some of your time steps, then do a backward pass before it's completed, and then it will run some more of your time steps, and then do a backward pass up to the point where you did your last backward pass. So for that, you would actually delete your time loop, put these in line with one another, and then you would do your update step. You would do that loop outside of your network so that you could update in your training loop. That's going to lead to a few problems, right? It's going to say something like in the second time you try and update, you'll get an error from PyTorch that says, tried to go back through computational graph, but it was already updated. To fix that, whatever your variable is, that it's often your membrane potential, you need a call detach to just like detach it from your comp graph. And then you can rerun time steps 10 to 20, detach, run time steps 20 to 30, and repeat. So I'm going to undo all of that because I would definitely get an error if I tried to show truncated backprop through time. Then a question was, why do we flatten here, but we're not doing it earlier? So we did flatten earlier, right? So previously we flattened, oh wait, shit. No, I see. Thank you for picking out my error. I am not meant to flatten the convolution, but I flatten when I pass it into the fully connected network. Thanks for picking that up. Awesome. So let's load that up into ConvNet. And same as before, define a loss, define an optimizer. This time I have a new network that I'm assigning to the optimizer. Change the learning rate to 1 times 10 to the -2 because whatever. Everything else is the same, right? So ConvNet, we train it, pass data in, initialize a loss value at 0, but then just pass in the spike recording. And we'll only run it for 100 iterations. Now, typically, the larger your network, the more iterations you need to really squeeze a benefit out of it. So I don't think this will actually outperform the fully connected network straight away. But if I was to run it for longer, it should do better. But yeah, see, at the very least, our loss is decreasing. So that's nice, right? Measure accuracy, this function is the same. I think it's all the same. Yeah, we're just passing our test set and our convolution in convolutional SNN into this measure accuracy function, doing the exact same stuff as before. And that's my, okay, 94%. So yeah, you run it for a bit longer, sweep a little bit more, and we should get some results that we're happy with. As a bit of a sanity check, I wonder if I can just check out the, I don't know, spike rec dot size. Awesome. So yeah, we have 25 time steps, 128 batches, and 10 output neurons. And so that's what we're playing around with every time we mess with spike rec and calculate accuracy. So that's a background to using snnTorch in 20 minutes. 20 minutes suddenly turned into like an hour and 15 minutes. We'll get there. I'll figure out. I'll sort my life out soon. God damn. This is actually how all my classes go. I like prep one class and then I ended up having to distribute that class over 3 classes. And then we hit the end of quarter. I'm like, shit, still got 70% of our material to go through. Don't tell my department chair we're recording this, damn it. So population codes. I think I'll be copy pasting a lot of stuff, or if you're interested, I can always like just pick up from where we left off. So for population codes, let's do like a bit of a hack, right? So I'm going to say num steps equals 1. I'm going to do a really small number of steps. So what our current goal with this population code is to try and train a network. And instead of doing it over many steps, let's just redistribute that cost to the number of neurons, right? So previously, we're training based on spike count. Now, if we didn't use population codes, then we'd have 10 output neurons and they would have 1 step to fire or not fire. That's really difficult to train. So what I propose that we do, no, that's bullshit. I'm not proposing to do it. Other people have proposed to do it. Other people that are much smarter than me have taken groups of neurons and counted up the spikes from that group, from that pool of neurons, and summed those up in shorter time steps. So if I say that my MNIST classes, now let's say that I have 10 classes, each class has 100 neurons, so that's 100 times 10, so 1,000 total output neurons, then in one time step, I can generate a maximum of 100 spikes. That's kind of easier to train. So that's what we're going to do. My number of outputs by default is 10, but I'm going to add like this population scaling factor of 100. I will initialize my layers. I'm just copy pasting from before. Num outputs, this time my output layer is going to be num outputs multiplied by population. So that's 1,000. So that's my initialized layers. And then everything else is just the same as the first network that we built, right? So I'm copy pasting this forward function. Indentations need to match. Perfect. Initialize our membrane, initialize our second layer membrane, generate our lists. Everything else is the same. We flatten because we're going back to fully connected layers, and I can get rid of that. So I'm going to load up my network onto into PopNet. Now, rather than deriving loss function and accuracy functions from scratch, I've already put in a bunch of stuff into snnTorch.functional, which I call SF, not to be confused with San Francisco. And that's going to have a few functions that let me immediately access things that can play around with population code. So when I say population code equals true, I then have to specify the number of classes. And all it's doing is kind of like, I'll quickly draw this up. It's like having some output layer where these guys, these 100 neurons are all generating spikes, and those spikes are just summed together. This is terrible. Those spikes are summed together to give me the total spike count from like my 0th index. But this is just like, instead of having one neuron trigger 1 or 0 spikes, I can now trigger anywhere between 0 and 100 spikes. So this might be my 0th digit. This might be my first digit. This pool of neurons might be my second digit. So that's all it's doing, right? It just takes a bit of boilerplate away. Gregor's asking, do I use population code only in the last layer or in the intermediate layers too? Well, if you think about it, when we're using gradient descent, we only really specify how the population interacts with our loss. So I don't know, I guess that population codes and intermediate layers, we're not applying losses to intermediate layers. So in this particular context, it's kind of irrelevant, I think. But if you did start projecting losses back to intermediate layers, then it would matter. But if I understand correctly, it doesn't matter here. Tell me if I'm wrong, though. It could be cool to iterate on this. Everything else is the same. Everything else is the same. I replace it with PopNet. Screw it, let's just run it. So it's not going to do great because it is only one time step, but the point is that it can train. So we can see that the loss to start with is a fair bit larger, but then, the fact that we can actually get some training going, even though we only have one time step, is kind of impressive, I think. So then we want to see what that means, right? We want to see if this accuracy can generate anything functional. In order to do that, I'll fly through this code. So we generate the spiking output from our model. So we pass our data into the model. We've already flattened it in the network, so that's that. Then we want to calculate our running accuracy. We have a function built into spike functional SF called accuracy rate. So we're using the rate of firing or the count, spike count, to generate the total number of correct labels. So spike rec, that's our output from the model. And we want to compare that to the labels. So all this is doing is like equating the two, just like before. But we also need to kind of hold this function's hand and say, yeah, we are using a population code and we have num classes equals 10. So by doing that, it looks at the dimension of the output layer, divides it up by the number of classes, and just well, not really randomly, but it just iteratively allocates this many neurons to one class, this many neurons to another class. And that's it for running accuracy. Running length, that's easy. We just get the length of the current labels and just expand on it step by step. Then the final step is to take the running accuracy, let's multiply it by 100 to turn it from a decimal to a, to a percentage, and divide that by running length. Accuracy equals, got too excited there. Let's run that, and then let's see the accuracy. Hopefully it's more than 10%. I think it should be. But yeah, the point is that if you were to do the same thing with without population codes, then your accuracy would generally plummet, right? So yeah, I'm going to keep moving forward. Tonic, I love Gregor and Fabrizio. Thank you so much for this tool. It's just this, it's the perfect tool for using data loaders in neuromorphic data sets. I'm going to say quiet so that we don't get a shit ton of notifications and print out messages. So Tonic is beautiful. Thanks for your service. We're going to load some neuromorphic data sets that are time varying. I'm not going to go through everything line by line, but we're going to load the Poker DVS data set. Let's take a quick look at what that is. It's like a dynamic vision sensor, which took a deck of cards and flicked through them really fast. And they've kind of extracted it into, so yeah, this is the event form. So it's really hard to tell, but it's really high speed. These are the events where I think the first is, what does this all mean? Yo, Gregor, what does this shit mean? So one of them is the spiking at the, oh, that's right. So the first entry would be the time step of the spike. The second and the third entries are going to be your XY dimensions. My man, he just answered in the chat. Thank you. And the final dimension is, I believe, whether it's an on or off spike. So on spike corresponds to an increase in luminance. Off spike corresponds to a decrease in luminance. And if like there's nothing there, then you don't generate a spike. So we also want to see what's the sensor size of the data they've given us. So we have two channels, one for on spikes, one for off spikes. Then the data set has, I think, been a little bit expanded from the default version of the data set to 35 by 35. If someone can like throw in a link to the original data set by Banabi, that would be awesome, just to give credit where credit is due. And likewise with Tonic, please do throw it. Yeah, Gregor, please like plug your shit, because it is a beautiful piece of work. We're doing some frame transforms on this data set, right? We're going to denoise it. So DVS cameras, dynamic vision sensors, are very noisy by default. So it's going to see, filter time is just a really neat way to look through the time steps of your data and just pluck out any isolated spikes and throw them out. Awesome. Thanks, Abdul. Yeah. Check out the database of the Poker DVS data set. And I'm using that because it's small and very easy to run in Colab. I then use a time window of 1000. So because event cameras are processing at like microsecond resolutions, that's just way too large for PyTorch and Backprop to handle. So we effectively clump these into bins. And here I'm saying, let's clump these into 1000 microsecond bins. We use a small batch size of 8 because the data set here is tiny. Then we use caching that I guess Gregor's painstakingly gone through. Do I have examples for time series forecasting with my library? I haven't. So I used to want to put in a bunch of neuromorphic data sets into snnTorch. Then I met Gregor and he was like, yo, we're already doing this and we're doing it a hell of a lot better. So I basically deprecated the data set data loading thing from snnTorch. But Gregor, I think you've got spiking Heidelberg data set, which is time series. Well, it's not you're not forecasting, but what are the other forecasts? Yeah, I don't think there's a common benchmark for time series forecasting in SNNs. There's the Glass-Mackey data set, which is common for reservoir computing. A fair bit of seizure forecasting work as well. If anyone has more insight on time series forecasting, please throw that into the chat. We cache those data sets. Oh yeah, so bam, we've got data. We've downloaded the Poker DVS data set. Let's run this code block. So that's going to cache the data set into something a lot more speedy to use. And if you have enough VRAM, then you can go, I think the line is memory cache data set, and that'll make things faster, right? Because then you're putting things on RAM rather than on your hard disk. Train loader, test loader, much like before. Any other interesting arguments? Batch first equals false, so that because snnTorch prefers seeing time as the first dimension, or as the 0th dimension. And then I'll just run this. Let's do a bit of a sanity check. So the size of each sample is 20. So what's 20? 20 is the number of time steps. 8 is the batch size. 2 is the other channels. 35 by 35 are my XY dimensions. 1, 0, 1, 0. So there are 4 classes. Can anyone, while I load this video, if anyone can guess what those 4, knowing that this is the Poker DVS data set with cards, can anyone guess what those classes are? Let's see. Yeah, so we've got clubs there, right? So the 4 classes are hearts, diamonds, clubs, and the other one, spades. That's cool. Let's train a network and see what we get. This time, let's go a little bit more animative. Oh, yeah, true. DVS anim. Oh, yeah, so if you go into the plotting, what's it called? Into the plotting function that I abstracted away, I used splat, the spike plot function, to animate this video, basically. So yeah, as long as it's done in the right structure, yeah, go ahead and steal that function for your own purposes. It's pretty neat, Can we download it? Yeah, I'm not going to download it. Recurrent SNNs, awesome. In recurrent, yo, is the 10:30 thing like a hard deadline? Because if y'all have to leave, by all means, like I won't be offended. I'll just keep going, right? Like yeah, Fabrizio, tell me if you need me to shut up, and I'll shut up sooner if you need. No deadline on this side. Sick. Let me check if like what my meeting schedule is like. Sorry about my terrible time management here. Oh, a bunch of missed calls. That's their problem. No, I'm good for another hour. All right, let's do this for another. No, I won't take up much more time. Let's use recurrent SNN. So what is a recurrent SNN? Well, I'll do a quick drawing here. So I showed you the recurrent. So we've got our input X. We pass that into, well, I guess we scale it by W, which we instantiated by nn.linear. Pass that into the Leaky integrate and fine neuron node. That generated the internal membrane potential, blah, blah, blah. We generated a bunch of spikes. Now, from there, a recurrent SNN can do something like this, right? It can take the spikes and loop them back around to the input. So it kind of adds that spike back to the input. And so you get like this extra dimension of recurrence. And it's been said in a few papers that this helps with learning more complex time series features. Okay, like I think we could do a bit more verification of this because there's already recurrent dynamics in the membrane potential of the LIF neuron. That's cool. So there's a few ways that we could play with this. We could take this S, we could take this spike and scale it by some learnable parameter V, and that's learnable. A few other things we could do, but because keep in mind, we have multiple LIF neurons. So on one hand, we could just duplicate this a bunch of times. So each spike just feeds back to itself. An alternative, which is maybe a little bit more commonly done because it helps with performance, is let's say that I have a bunch of LIF neurons. Each of them generate their own spikes. Each of them generates, so we'll call this S0, S1, S2, and so on. Then what the alternative approach is to get just like, rather than having a dot product of spikes, a dot product of spikes with their own unique Vs, with their own unique V values that are learnable, it's just pass all of these into a linear layer, have them all kind of like overlapping and going through a bunch of like, I guess it would be a sort of matrix vector mult. I don't really know. And the output would have to match the dimensions of this input here, and it would just get added to that guy there. So of course, you're introducing a little bit more computational complexity by including another NN.linear layer, but that's something that people like to do, and that's cool. I'm going to clear this all. And so yeah, let's see how we actually construct this. So number of inputs, 35 by 35 XY dimensions by my channel size by 2. I'm going to just do fully connected recurrent SNNs. Number of hidden layers, I'll go a little bit smaller, 512. Number of outputs, four classes, hearts, spades, clubs, and the other one, diamonds. Beta, 0.9 arbitrarily. I will go ahead and copy paste the initialization of layers and just show you how it's different from what we've done before. NN.linear, the linear layers are all the same. Instead of going leaky though, we now say recurrent leaky or R leaky. So beta, same thing, 0.9. We have a decay rate that doesn't matter. By default, we're using the more complex recurrence where the spikes are all projected back to an NN.linear layer inside of R leaky, and that goes back to the spiking layer. So there is a NN.linear subsumed within recurrent leaky. Because of that, we need to specify how large that linear layer is. And the correct number, there is a correct number. We can't just be arbitrary about it because it has to, the output of that linear layer needs to match the input of the spiking layer so that they can be added together in that recurrent loop. So linear features is just the same as the dimensions of the previous layer. So linear features equals num hidden. And then the next two lines are the same thing. There is a way to play around with this. So alt to alt, I think that should be a function. Yeah, so what I call that is a recurrent SNN with alt to alt connection, because all of your spiking neurons generate spikes. They're transformed by a linear transformation, and then they're projected back to every spiking neuron in that layer. If I don't want to do that, if I just want a one-to-one connection where every neuron only is recurrent back to itself, I just say alt to alt equals false, and that is that. Then I don't need to specify the number of linear features. As an aside, if my input data is not linear, if I instead am using a convolutional structure, so let's say this is nn.conv2d, then instead of saying linear features, then I would have to say conv features or conv2d. Actually, I don't remember, to be honest. Let's see. Which one is it? Okay, I can go into the docs. You know what, in the interest of time, I won't go there, but check the docs. There's an example in there. But you have to specify your number of channels, the kernel size, and there's going to be padding in the background to ensure your output convolution matches the input feature map so that they can be added together. Hopefully that makes sense. So linear features equals num outputs. No, sorry, num hidden. Awesome. Then my forward function, again, I'm going to copy paste this. Won't do this from scratch anymore. Are there any differences? Yeah, some minor differences. So now we init R leaky instead of leaky, and because we now use spiking as a recurrent variable, we have to initialize that as well, because every recurrent LIF neuron has to have an initialized spike and an initialized membrane as well. So let's see the forward function. This time we're using time varying data. So we have to index into, great question. So a 1D convolution supported for R leaky? Not really, no. I'm sure there are ways that you could hack it, but I have never tested it. And that's purely because 1D convolutions are typically known for convolving over a time dimension. Of course, it doesn't have to be a time dimension. That dimension can be arbitrarily defined, but we assume that with spiking neurons, you feed data in sequentially one by one. And so we haven't seen too much 1D convolutions combined with recurrent SNN type structures. I'm sure that there have been a couple of papers that do play around with it though, but it could be really cool to open that up as an issue or to contribute to SNNTorch and test out under what cases does it make sense to merge these things. So we iterate through every time step of data, and that iteration through time, if your input data is what would kind of preclude 1D convs from being applied over time, because you only have one time step at a time available to you. So yeah. And here in my range, I'm just saying that rather than defining the number of steps, I'm letting the data define the number of steps, because the dimensions of my X data, the number of steps, like time times batch times, what was it, 35 by 35 by 32, right? So that's, I cannot do that in my head, but just the number of inputs, right? So we're checking what the length of time is. And so that's going to be the number of time steps we use. We flatten it because we're using like a fully connected structure. Now, LIF1 has the input, and in addition to the membrane, it also has to pass the spike back into itself. So that's the only difference. Everything else is much the same. When we call RSNN into RNet, and that's loaded. See if there's anything else that we need to change. RNet is good. Everything else is the same. RNet. Awesome. Let's do everything that we've done. No errors. Love to see it. Okay, so the loss is going down. There are a lot more parameters. So again, this usually would require, okay, so I think I terminated pretty early. Because the data set is so small, we didn't even reach 100 iterations, right? So I don't know if this will work. Okay, so the accuracy is 94%. It is a really easy data set to solve. So yeah, not a big deal. Like, it's not like we've solved poker for the research community. But yeah, awesome. So that's recurrent SNNs. Spiking convolutional units. Look, go to the cheat sheet. I won't code all of it, but the vibe is that we initialize we initialize LSTM layers. If you want to do sequential LSTMs with a spiking layer, just use SLSTM. If you want convolutional spiking LSTMs, then sconv2D LSTM. You specify the size of your convolution, but that's going to be a convolution that changes over time. Set your max pool. Then here I've got a threshold of 0.1, just because in practice, look, I'll copy the whole thing. So in practice, what I have found is, so number of outputs for beta. So do we even use beta? Yeah, we do. What I've found is that the LSTMs have this tendency of, because of the way the activation functions in an LSTM block are used, we typically don't see neurons that hit the threshold effectively. It's kind of hard to promote LSTMs to go too large because they've kind of been normalized in a nice way. So I found that it was very difficult to train things at first. Then I just looked at my output of spiking and there was no spikes. So I just dropped the threshold down to like 0.1. I think by default, the surrogate gradient is also arctangent. It might be a straight through estimator. I don't remember, to be honest. But yeah, so everything else is the same. I won't run this, but the principles are all the same. We can get rid of this as well. But yeah, the spiking convolutional units take in an input spike, and they take in two state variables, which I've called synaptic current and membrane potential. So this is theoretically, well, these two are theoretically the same. Actually, all of them. Yeah, all of them are much the same as a typical LSTM. So nothing really exotic about that. It's just a spiking, it's just an LSTM with a threshold at the end to make it spiking, such that those ones and zeros can ideally sparsify interlayer communication. Let's forget that. Don't worry about it. If you run it through, I don't think it'll actually perform too well because this needs a bit more of a sweep. Precise spike timing. So I haven't run through any of this code yet, but there is a function in there. So previously we were doing rate codes. We were using losses with cross entropy. In order to mix that up, spike functional has two variations of loss functions that target spike timing. So if I want a network, if I want a neuron to fire at a particular time, then I can either use MSE temporal loss or cross entropy temporal loss. So MSE temporal loss will just look at my output neurons, but by default, what it does is look at my output layer, and the correct neuron is going to be promoted, is going to try and fire at the 5th time step. If I can remove this, and then it will try and fire at the 0th or the 1st time step by default. All my incorrect neurons will try and fire at the 20th time step. And then you would correspondingly use an accuracy function, sf.accuracy. Previously, we used accuracy underscore rate. Now we can use accuracy temporal. So what that does is take the output spikes and look for the first spike in a tensor and basically say, hey, this neuron fired first, therefore that is our predicted class. It doesn't look at how many times it fired anymore. So this is a little bit more experimental, and I had to kind of come up with my own little tricks. I will maybe not go through what those tricks are exactly here, because I don't think they've kind of been used anywhere else. They're massive hacks, and the source code is a little bit challenging to go through. But yeah, so that's what MSE temporal loss does. Cross entropy temporal loss just tries to, I guess, maximize values. It tries to maximize the time step at which incorrect neurons fire, so it just pushes them all the way to the end. And I've kind of maximized a negative value or a 1 over inverse value to get correct classes to fire earlier. I won't go through this training loop, but it does take a lot longer because we use a lot more for loops to kind of iterate and see where the first spikes occur. In practice, this will lead to sparser activity, but at the cost of much longer training times and generally much worse accuracy, because there are a few challenges associated with it that I won't go through at the moment. Finally, yeah, look, if we want quantized networks, so say you've got edge hardware, say you've got an FPGA you want to run on, or you want to load up a neural network on a microcontroller or something like that, what we do is Xilinx, AMD, they have developed a very nice library called Brevitas. Brevitas lets you kind of plug and play a bunch of neural networks. So previously, we used like nn.linear. This time, we're just going to replace, did someone say FPGA? Fabrizio's time to shine. Instead of using nn.linear, we call qnn.quantlinear. You do the same thing, number of inputs, number of hidden units. This time, we can also specify the bit width of each weight, right? So quantlinear instantiates the weight bit widths. It instantiates weights, so we have to quantize those. Like if we have a limited range of bit precisions, then maybe we want 8 bits per weight or 4 bits per weight. And I think by default, PyTorch will jump to full precision, so 32-bit floating point values. You can use mixed precision, that usually doing computation with floats is a little bit more expensive than doing computation with fixed precision integers. So yeah, we run with 8 bits, and it uses a straight through estimator in the background because quantization is non-differentiable. So it's kind of like abstracting non-differentiability away in the same way as SNNTorch and surrogate gradient descent and all of that. So literally it's just a matter of converting nn.linear into qnn.quantlinear. That's pretty neat. I don't believe the output of these layers are going to be quantized. So if you need to quantize activations, then that requires calling additional functions. But yeah, everything else is the same there, which is really nice. You might also, so there's a few things that can be quantized. So weights are easy. Activations, relatively easy with just calling other quantization functions. But there is other stuff that might be perceived as cheating. So spiking is 1 and 0. So that's as quantized as it gets. It's a binary tensor. The membrane potential, on the other hand, that is going to be a floating point value by default with PyTorch. So again, these are all still in floating point, but they're just represented as kind of like a step function applied to a floating point. So it's kind of like if you needed to train something that's quantized, then this is what your performance would look like. This is what your accuracy would look like without actually having to go through the hassle of rewiring a GPU to work with 8 bits. Okay, so that's kind of like the ethos there. Now, membrane potential is not quantized by any means here. So how can we fix that? Pretty easily. I have I've got a nice function in snnTorch.functional from snnTorch.functional import quant. So quant is just quantization. I can instantiate some rules for how I want to quantize my state quantization. So num bits, let's say 8. Uniform, so there's different modes of quantization. So by default, my quantization is going to be uniformly sampled. So it's like if you quantize based on steps, uniform lets you have those steps to be equally spaced apart. Some people have done a lot of research on weight quantization and non-uniformity, where they observe that there's way more weights centered about 0 or about certain values. So they have more values allocated to things that are close to 0, and they have like larger steps away from 0. So yeah, same mindset. Uniform true means that you go from like a negative threshold to positive threshold uniformly. If you say false, then it kind of the distribution, it goes exponentially towards 0. But there's no reason why it has to be exponential about 0, right? We can also center the distribution about the threshold. So that will have, because if you think about it, it really matters what the precision is around the threshold, right? Like if I have a threshold of 1 and my membrane potential is 0.9, if I was to quantize that to 2 bits, 4 bits, then that could easily trigger a spike. That could be determinative. So I've included a feature that lets you shift that distribution to the threshold instead. I don't know what works best. I am still figuring it out. I haven't experimented with this feature much, but I think it's pretty neat. And so we take QLIF. So I have an undergrad student that's doing some cool stuff, and he's actually found that setting the negative, the floor of your quantization parameter to be 0 works a lot better than setting it to negative threshold. So that kind of indicates that inhibition doesn't matter too much when we use backprop. And the only difference here is we apply state quant equals QLIF, right? So QLIF goes here, state quant, and then automatically membrane potential will be some quantized value. And that's literally how to quantize your membrane potential without having to think too hard. I think that's kind of neat. And then everything else is the same. Like I only had to call one function and pass that as an argument into my Leaky, integrate, and fire neurons. And that's basically it for state-based quantization. So now I have weight quantization and state quantization. Yeah, currently writing a paper about that called SQUAT, so state quantization or some dumb shit like that. Oh yeah, so I did everything in the same code block, but yeah, that is what it is. Look, 1050, I've talked enough. Hyperparameter optimization with Optuna. Please like, share, and subscribe. And you can yeah, we can do some session another time. But yeah, I think that's it from me. I've overstayed my welcome by way too many hours. So yeah, thanks for your time. Thanks for sticking around if you managed to last that long. So yeah, I appreciate that. If you have any questions, throw them my way. If you have features that would be cool to add in. Also, the Colab Notebook has non-functional hyperparameter sweep stuff that you can play with yourself and try to get it working. A couple other things that I'd like to briefly mention. If you're interested in becoming a contributor, look, there's so many things that would be cool to add. Neurons with adaptive thresholds, haven't bothered with that. Different types of neurons. Hey, write up tutorials. I think the tutorials are part of why this got onto people's radars. If you want to do tutorials on new learning rules, how to add that, how to use snnTorch or whatever other Python libraries out there to do new learning rules would be cool. Combining it with other stuff. Someone mentioned the forward algorithm. That's pretty sexy. Pizza by Georgia. That'd also be pretty awesome. Dendritic computation. That'd be nice. And yeah, a few other opportunities for neuromorphic folk out there. So one thing that's cool is Telluride, the neuromorphic cognition workshop in Telluride in Colorado is open. So some applications can be made by looking at this website. Topic areas. So I'm actually hosting one of the areas. My catfish photograph here with my former grad student Peng. So she's killing it in a neuromorphic startup. And we're focusing on open source neuromorphic hardware, software, and wetware. So it'd be awesome if you made it down to that. Got a lot of cool projects. We're going to tape out an actual neuromorphic chip. Even if you don't know anything about silicon, you will get some silicon space, and I will train you up to get some something taped out, which would be cool. Trying to set up a few other projects. Fabrizio, HLS for NM, going to force you to contribute to that. Gregor is working with SynSense, and he's going to do some cool demos with Spec and Xylo. Bunch of other stuff. It's going to be fun. That's Telluride. A lot of cool. It was the coolest part of my PhD when I went in 2018. I'm also an associate editor of APL Machine Learning, so check that shit out. It's pretty cool. It's a new journal. It's all about how to apply machine learning in physics and how to use physics in machine learning, and how to use physical systems. So spiking neural networks and neuromorphic computing fall under that umbrella. So if you're doing any research in the SNN neuromorphic space, consider submitting to APL Machine Learning. Definitely looking to some high quality contributions there. Likewise, I'm also guest editor of a special issue of the IEEE Journal on Emerging Topics in Circuits and Systems, bridging the neuro AI to neuromorphic gap. Neuro AI, all about using AI to model neuroscientific-ish systems, brain systems, and neuromorphic is all about trying to make AI a little bit more efficient using brain-inspired principles. So smushing those two things together makes a lot of sense. So deadline for that is the 31st of May, I think. What else have we got going on? And I'm also going to be delivering a tutorial at ISCAS in this year. A lot of handsome people. These are the most handsome people. I'm going to co-deliver that with Charlotte Frankel at TU Delft on how to build open source neuromorphic hardware and algorithms. So it's going to be like a watered down version of this talk, plus how to build chips or neuromorphic chips. So someone's asked about deployment. Come to that tutorial and I'll tell you how to. Honestly, we're figuring things out. The most logical approach would be take an snnTorch model, save it as a .pt file, compile that as an ONNX file, throw that onto whatever platform you want, because a lot of things, I guess ONNX is just a really nice intermediate representation of pretty much any neural network Python library out. So yeah, not very experienced on that, but yeah, not outside my own chips at least. So yeah, that's all I want to talk about. Hey, thanks for your time. Thanks for listening to me ramble for 700 hours. So yeah, Gabrielle is asking, so yeah, neuroscience, SNN, neuromorphic networks, and neuron fired to all. Social networks are events that can be cyclical, complex between entities, a subset of potential connections. I'm getting like a bit of a graph network feeling over here. Is there a way to represent those sociology network events with SNNs? Yeah, definitely. I think there's been a fair bit of work on, so I'm just going to kind of abstract all of that into graph neural networks, because I think that's the topic that deals with weirdly structured connections rather than dense and convolutions. So it's a little bit more unstructured. Yeah, there's plenty of work on spiking graph networks. I imagine that the way to simulate such things, if you wanted to do it from scratch, you would be stuck with nn.linear and all of that, but then you would generate masks to kill a bunch of connections, and then you would generate a bunch of skip connections. And by doing that, you could kind of emulate graph networks in a very hacky way. And then you would just put spiking nodes right next to your linear nodes. I'm not familiar with the graph network libraries that are out there, but yeah, there's definitely a lot of work that already does that. Fabrizio, do you want to chime in and take any more questions? Damn, he's gone to sleep. I guess I can host myself now. Yeah, all good. Really good question. Fabrizio, what are you doing? Legitimately, like, look at this guy. His screen is dark. Microphone's dead. He's just gone to sleep on me. I mean, do you want to just chat and I can wrap myself up? Thanks so much, Jason Eshraghian, for that incredible talk. That was, no, I'm just kidding. No, you're still muted. No, I hope that was useful. And yeah, feel free to reach out to me if you want me to organize like I don't know, something that goes into more detail on the stuff that I had to fly over, because hyperparameter sweeps, very important. That changed my life. It would have been good to go over that. Yes, there we go. He's back. No, he's not. He's not back. I'll stop sharing at least. okay, whoever that builds the spiking neural network that can lip read Fabrizio, then then I will give them snnTorch.
Maybe
Okay.
yeah, now you can hear me. Okay.
Okay.
It's always Zoom that gives so much emotion. So it was nice. The talk was really, really nice. I was really entertained. So, and I think they were too, by the way. We had a little bit of audience. So we will stop here, basically.
Yeah, sounds good. Any other questions, feel free to just shoot them through directly. I think you've got the Discord channel. I'm somewhere there. Easy to find me.
Yeah. You can reach us on Discord. We have also a LinkedIn group, even if we don't not look that much at that, but mainly on Discord, mainly memes and shitty code, basically.
Awesome.
Okay, then.
All right.
So,
hope to see you at the next Open Neuromorphic event, huh?
yes, the next Neuromorphic event will be on the 21st of March, and we will have Catherine Schumann from the to talk about evolutionary neuromorphic systems. If I'm not mistaken, it was that was the actual title. So as usual, we will stream it on Zoom, and also as this talk, also that one will be put on YouTube as soon as we have the recording. And that's it. We plan on keep doing talks once a month. We'll see, and as much free time as we have, more or less. And that's basically it, I think.
Beautiful. Thanks a lot. We'll see you soon.
See you soon. Bye-bye. Bye, everyone.